Hello and welcome back to another VMK in the game development series. In this VMK, we're going to take the parser that we developed in the previous VMK and start putting it into our game engine. Now, this process of putting the parser into our game engine is going to be a little bit of an adventure because it's going to span multiple VMKs to get it all incorporated. So in this video, we're going to start off by going into the scene class and creating a new class that will handle how the parsing will occur. Basically, it's going to be a data dump of what we did in this Caligari parser project, VMK 32C, D, and E. So we're going to put that into our game engine, but there's going to be a lot of pieces that are going to be missing after you finish this VMK. So when you finish this one, you still won't be able to build and render anything to the screen. As a matter of fact, it's going to take a number of VMKs after this one before we can get our code back to a state where we can actually render things onto the screen. So please be patient, but all in all the work is going to be well worth it once you have this code implemented. So to get started, let's go into our game engine, and let's start off by going into our scene.h file here. What we're going to do is create a function that will be called whenever we want to parse a Caligari file. So let's see. Let's put it in here. So I've called it load Caligari file, and we're going to specify a file name. Whenever we call this, this function is going to be responsible for parsing the file, figuring out what's inside of the file, associating, the poly-H data, the material data, the shader data, all that stuff. It's going to group all of these into sort of structures in memory so that we have all the data that we need. And then it's also going to go through and actually populate the scene graph with all the information that we load in from the Caligari file. All of that work is going to happen in here. We're not going to actually write this whole function in this video, but we will do the part that does the parsing, since we've basically finished that in the previous VMK. So let's save that and go into our scene now. And inside of our initialize, you'll notice that at the bottom here we load in our default position for the eye, our headlight, and then we have a load level function here that loads that LVL file, which we parse ourselves. This is the ASCII parser that we use. Well, now we're going to add in here some extra code. And we're just going to call that new function load Caligari file. And I misspelled it. Let's try this. And it has one parameter, so in here you would specify the name of the file you want to load. So for instance, it would be something like resources / models / I don't know, mech.cob. And then if you had another file that you wanted to load, you would just go and do something like this and then specify the name of the other cob file and so on. So you'd continually call this function to load in all the cob files or scene files, whatever you want to load in. This function is going to be responsible for populating everything inside of the scene. One thing I do want to mention here is inside of our game engine, you'll notice that inside of our build debug, this is where our program will be running from. So we'll point inside the resources, and then I mentioned here we're going to create a folder called models, so we might as well do that right now before I forget. We're not going to put anything in here right now, but after we get the parser up and running and we actually want to see stuff on the screen, this is where we're going to start putting stuff in. You can put it anywhere you like, but I just sort of started grouping our models into a separate directory. Okay. So now we have to write this load Caligari file function. We're going to put this load Caligari file function right below load level. So let's go in here, load level, and scroll down to the bottom, and this is where I'm going to stick it. load Caligari file. Now, as I said before, we're not going to finish writing this code in this VMK. We're actually going to finish it in a few videos down the line, but just realize that there is more to come. There's actually more code will go here. There's like 200 some odd lines of code that will go down here, but just to keep things sort of modular, we're going to do things piece by piece. Now, looking at this load Caligari file, you'll recognize it as being the main function from our previous VMK. We accept the file name that we want to load, and we create a file pointer. We try to open up the file that we passed in here as a binary file, and if we can open it, then we continue on down through. Otherwise, we generate an error message using our error handler saying cannot open whatever the file name is here. If we can't open it, what we're going to do is create a new variable here of this type called Caligari file. And in this video, we're going to be focusing on writing this class here. So we haven't done this yet, but basically what this class does is it accepts the pointer to our error handler and the file name. So it's going to have both of these, and we're going to call a function within it called parse. And parse is just going to go through using the file pointer that we opened up here and parse that Caligari file for us. After it's done, we're going to call fclose, and that's basically all it has to do. The Caligari file class is going to be very similar to the code we wrote in the previous VMK that does all the parsing. What this class is going to do is actually store all the important information that we need from the binary file into separate variables. So let's go in and let's see here. Under our Solution Explorer, what we need to do is first we need to create two new files here, one CPP and one .h file for this Caligari file. So we'll just click on this, go into here, we want to create a new CPP file, and it's going to be called Caligari file. And we also want to create a .h. And let's start off with the .h. Okay, so here we go. At the top, we're going to include something called Caligari mat1, Caligari polyh, and Caligari shbx. These are three different classes that we're going to be creating in the next following VMKs. And these classes are going to contain all the material data, all the polygonal data, and all the shader data. But for now, we're just going to assume that these already exist, so we're just going to move forward. Our class is called Caligari file, and as you've already seen, the constructor takes a error handler and the file name that we want to be parsing. It also has a function called parse, which accepts a file pointer, and this parse function will do all the parsing of the binary file and fill in all the data into these classes here. The member variables for this class are 3 vectors, and each of these vectors contain the appropriate data for each of these data types. Since we don't know how many different kinds of materials or shaders or polygonal data pieces are going to be inside of a binary file, what we need to do is create this dynamic vector here, and every time we find a specific piece of data that we want to save, we're just going to push it into this vector. And then we're going to have all the data we need for a specific file inside of this class. We have some private member variables here, the error handler and the file name, just as a reference so that we can use it later on as well. So let's start off with the constructor. At the top, we need to include stdafx.h and Caligari file.h, and here we have our constructor. It doesn't really do very much. All it does is it takes our pointers that we pass into our constructor here and saves it into our member variables. Our destructor, though, does have a little bit of work to do. Since all of the data that this class is going to be storing is dynamic, we need to make sure that when we're done using this Caligari file class, we deallocate all the memory that gets allocated dynamically. So to do that, we're going to go through each of the vectors that contain all the poly data, the material data, and shader box data, and delete all the data that's stored inside there. So you see here we have a for loop that goes through the entire array that contains all the poly data, and we call delete for each Caligari poly H pointer that we have stored inside of that vector. We do the same thing for the material, and we do the same thing for the shader box. Now we go on to the real meat of this class, and that's the parse function. You'll recognize this parse function as being very similar to the parse function we wrote in the previous VMK that parsed all the data from the binary file and displayed it to the screen. But this time, instead of displaying it to the screen, what we do is we store it inside of each of these array structures. So at the top here, we need to create a file header, and this is of type Caligari header. And since we haven't defined this inside of our game engine, we need to make sure we do that. Unfortunately, these structures are stored inside of the, let's see here, it's stored inside this file here. We're not going to be writing the details of this file in this VMK, so you'll have to wait for the structure definitions till I make that video later on. But you've already seen the structure of each of these data structures from the previous VMK. So I'm not going to go into the details of what each of these represent. They're exactly the same as they were in the previous VMK. Now let's see what we do here. We read in the file header, same as we did before. We do a check to make sure that this file that we're reading in is actually a Caligari file. And you'll notice that there was a slight error in the previous VMK where this number here was a 1 rather than a 2. The code itself would still work because the difference between these two values are LH or HL, so we were only comparing the first character rather than both characters, which is fine. You don't have to change it, but just to keep things consistent, I changed it back up to 2. Anytime that an error is generated, we now use the error handler to show the error messages to the screen. So here we say that the file name that we've specified is not a Caligari file, we show the message, and then we reset the error code. And we return false from our Caligari parse function. Next thing we do is we make sure that the file format is in binary rather than ASCII, so if it's not, we generate an error message. Then we use this chunk header member variable to store all the header information about each of the different chunks that we're going to be reading. Inside of the while loop, we call fread, and we fill in the data for the chunk header, and then depending on the data that's inside of the chunk header, we decide what to do with it down below. So we have the if statement here to do a comparison with poly-H, with end, with the material one, and with the shader box chunk types. If it's not any of these four, then we just skip over the data appropriately, and then we continue on down through with the while loop. Once we finish going through this while loop, we just return, and then we're done the parsing. So let's go inside of these if statements here, and they're going to be very similar to what you've seen in the previous VMK, so I'm not going to go into very much detail here. I'm just going to point out the major differences between the code here and the previous code you saw in the previous VMKs. We first get the name of the current chunk, so we get the number of characters that the name has. We allocate memory for the name. We get the name, and then we null terminate the name itself. After we have that, we then create a new pointer to this Caligari poly-H data type. This is a data type which we haven't created yet, but this is coming up in a future VMK. This Caligari poly-H data type will have a constructor which we pass in the current ID number for this chunk, as well as the parent ID number and the error handler. We use these things to reference the data that's going to be stored inside poly-H for later on. Then what we do here is, I should point this out. If this guy here fails, whenever we call the new operator, we need to make sure we deallocate the memory which we allocated up here for the name, because we already used the new operator up here. So if this guy fails, we need to deallocate that memory. If it doesn't fail, we continue on down through. And what we need to do is make sure that the name that we loaded in from the binary file doesn't have any spaces. It is possible to save names that have spaces in them. However, inside of our game engine, we don't want to have objects named with spaces in the name itself. So what I do here is I replace anything that has a space with an underscore here. So we go through, replace all the spaces, and then after doing that, we use the polyH's class here to call a function called setName, and we pass in the pointer for the Caligari name that we allocated new memory for up here. So in essence, we're saving the name of this polyH chunk inside of this polyH data type. We then go and parse the local access data out of the binary file. So we call fread here to read in some data. And if something here fails, we need to delete the polyH data type, which will clear up any memory that was allocated using the new operator, and then we return false. If nothing here fails, we continue on down through, and we don't use this data, so we don't save it. We then go and get the current position data from the binary data inside of the file. We need to allocate a data type here called Caligari chunk transform. We fill it in with some data, and if there's an error, we go and delete the polyH data. Otherwise, we go and save the polyH data that we just read in for the transform into this data type structure here using the set transform. So these are all different kinds of functions we'll be writing in the future. We haven't written these yet, so don't worry too much. Next, we look for the local vertex list. First, we get the number of vertices that are contained in the data, and then we use a for loop to get each vertex information from the file. So here, we create a vector 3 called v3, and we call fread, and we pass in the address of the vector's first parameter here. We say we want to read in 3 floating point numbers, and after we fill in the data inside the vector 3 guy, then we can go in and call addVertex for this polyH data here. So whatever we read in, we're going to save inside of our class here. We do the same thing for the UV index list. We call fread, we get the number of UV indexes, then we go through a loop here to actually save the data inside of the polyH structure. So here we read in the data for this specific UV. We then call this function addUV, which is part of this polyH data structure, and we pass in the vector 2, which is up here. We do something similar for the face list. We first get the number of faces that are contained in the file, and for every face, we're going to go through this for loop here and determine whether the face is actually a face or whether it's a hole. This time, we also make sure that the number of vertices for every face is equal to 3. If it's not equal to 3, we generate an error message saying error parsing polyH, face number whatever has this many vertices, which will not be 3. We must triangulate this face first. And then we cancel out. So if we find something that does not have 3 vertices per face, if it has 4 or 5 or more, then we basically stop parsing and exit out of the function here. So make sure that everything that you're parsing has been triangulated, because all the code later on depends on us having triangulated faces. Then we do a check here to see whether the current face is actually a face or a hole. So if it's a face, we go into here and we create a new data type here, Caligari face. We read in the material ID number for this face, as well as the UV vertices and the vertex indices for this specific face. And then we call an addFace function, which is part of polyH here, and we save the current face's data into polyH. If it's a hole, we just skip over it because we don't save any information about holes. After doing all that, we're done with the polyH data, and we can save it now inside of this array here. So to do that, we basically use this guy, push back, and we push back the current polyH that we just finished filling in all the data up here. for the faces, for the UVs, for the vertices, and so on. All that data that was saved up above is now pushed onto the array, which is called m_v polyh. Last thing we need to do is check for these additional flags. So if they exist, we need to skip over them so that the next item through this for loop, we're pointing at the right location to the beginning of the next chunk header. Okay, going to the next section. If we parse this chunk header, which is end with a space after it, then we just break out of the while loop because we're done. There's no other data we need to handle. If we have material 1 or mat1, then we know we're using material data. So again, we create a local variable here called material, and we read in all the material data that's inside of the file, one step at a time. Then we create a new pointer here to this pMaterial data type. We call the new operator, and we pass in the chunk ID as well as the parent ID into this material1 guy. We don't need to pass in the pointer to our AR handler because when I finish writing this code here in the next VMK, you'll see there really isn't very much possibility of making errors in there, so I didn't bother passing in the AR handler in here. If there's an error creating this new memory here, then I generate an error message, show it to the screen. Otherwise, we continue on down through. And if we do continue, then what we do is we take the material number, which was read in here, and we save it inside of pMaterial. And we also save the color that was read in over here. So we have the red, green, and blue values. So I pass those in here, red, green, and blue, as well as the opacity, so that we have an alpha channel for all of our colors. If the material is a faceted type that is set to be smooth, then we set the smooth shading value to be 180 degrees, which is equivalent to pi. So we pass in pi here into the function called setSmoothing. You'll notice that we have a function called setSmoothing, which basically tells this material that we're going to be using what is the angle between the faces that we want to smooth. And I'm specifying this angle in radians because the value that we're going to be using later on has to be in radians to do all the math. So to prevent us from having to do some conversions later on, I actually save the smoothing value in radians right now. If the facet type is autofacet, then that means that there will be an angle that was read in here, auto angle. So we need to take that auto angle value, convert it into a radians. So we take that value, multiply it by pi divided by 180 degrees, and that gives us the equivalent value in radians, which we then call setSmoothing on. If it's not one of these, then we know that the face is faceted, so we set the smoothing angle to be equal to 0. Then finally, we also do some checks for the optional parameters. You remember there was environment map data, texture data, and bump map data. So we need to make sure we do some checks for all of these. If we have environment data, we skip over the appropriate chunks here. If we have texture data, we call a function here called setTextured, which sets a Boolean value inside of this data type to let us know that there will be a texture associated with this material. And we just do this because later on when we're constructing our material node and our shape node, all of that stuff will be helpful to know whether we have a texture or not. So because we know whether we're going to be using a texture or not here, we can set that flag ahead of time inside of the material structure. We also skip over all the data that's associated with the texture, since we're not actually going to be reading in which file we're going to be using if we are using a texture. That will come from the shader chunk, which I'll show you down below. Also, if we have bump map data, we need to skip over that data, and after doing the checks, you'll notice that at the end we always read in 2 bytes past the current location, so we need to reverse by 2 bytes. That's what we do here. And then we take the material data that we just finished filling in with data up above and push it onto our array, which was located right here. So that's for the material. The last thing is for our shader box. So if we have shader data, first thing we do is we create a pointer to our shader structure. And this shader structure also takes in an ID number for our chunk as well as for our parent. And what we do is we go through a for loop from 0 to 4 to, well, 0 to 3 actually, and we read in the 4 different types of shaded data that's saved in here. We have color, transparency, reflectance, and displacement. And every time through, we have a shader class type, so we read in that. We also have a shader name, so we read in the length of the name as well as the name itself, and then we null terminate it. We read in how many parameters this current shader data has, and then for each parameter, we go through and we read in the name of the current parameter. If there's any error messages, we make sure we delete the shader box data type that we are working with up above, and we just exit. If there is no errors, then we continue on through and we start filling in all the data. So we read in the name of the parameter, we null terminate it, we read in what kind of type it is, and then depending on what type it is, we go into this switch statement. Now, there's only a few different types of data structures that we're going to be saving. We know by using the parser from the previous VMK what sort of data to expect. And for the data that we are expecting to be saving, we have a special function inside of our pointer to our shader box data here that we call. If our data type is equal to 1, that means we're going to be getting some integer value data, but we're not going to be saving that, so we just read in the value, but then we continue on through. dword we're not saving. Floating points we might be saving, because the floating point numbers would be things like our shininess. So if that's the case, we read in the value here into this parameter here, fValue, and then we call save parameter, which is part of this structure here. And we pass in the class of this current shader, so that's one of these numbers located up here. Where was it? Right here. It's either going to be 0, 1, 2, or 3. And depending on which one it is, it's going to tell us what kind of data, color, transparency, reflectance, or displacement that we're reading in. So we need that information. We also need to know the shader name, because that's going to tell us what kind of data to be expecting, or at least this floating point value is associated with what kind of data. It has a parameter name, which we also need to know, and we need to know what kind of type of data this is, because we're going to be reusing the save parameter function multiple times. So we need to specify the type as well as the value. And this last parameter is actually a void pointer, which we pass in here. So you'll notice that when we're using the float, we're passing in the address of the float, but then down below, whenever we're using this integer here for the boolean, we're passing in the address of the integer. So we can pass in all different kinds of data types into this last parameter, because we pass in the data type here, which we can then decode inside of the save parameter. We did something very similar inside of the ASCII file parser whenever we used the, I think it was called something like find keyword. We had a void pointer that pointed to all these different kinds of data types, which we then used inside of the function itself. So anyway, floating point numbers we will be saving, doubles we will not. Enumerations we can skip over. Booleans we might be saving, so we also call save parameter here. Color values we will be saving, so we call save parameter here. Vector we skip over. Point we skip over. Strings we do need to save, so we get the length of the string, allocate new memory to it, read in the value, null terminate it. After doing all that, we then call save parameter and we pass in the pointer to our name that we just finished reading in. And let's see here, shader we don't save, short we don't save, words we don't save, bytes we don't save, color 4 we don't save, and that's it. So if there's anything else, we generate an error message here saying unknown shader box parameter type ID, show that to the screen, and after doing all that, we just delete the memory that we allocated for the parameter name, since we're done using it already, and we need to also read in or skip over the flag parameter, which should, I think, be set to 3, and we also delete the memory that was allocated with the shader name. So after doing all of that, we can then go back through to the top here, which is for the next for loop, which is the next different type of shader type. So after going through all 4 of them, we take all the data that was saved inside of that shader box and we push it onto our array, which contains all the data for our shader box types. And after that, we're pretty much done. So that's a quick lesson in terms of parsing the Caligari file. Now, if you're very observant when I was going through this code, you would have noticed that I did something that violated one of our previously written functions. And if you scroll up to line, I think it's 171. Where is 171? 171, right here. You'll notice I used the address of vector3's member variable called m_f, and I passed the address 0 to it. Well, if you go into vector3 here, vector3.h, you'll notice that for the member variables, we just have these 3 guys. We don't have something called m_f. And that's because I actually had to modify our vector3 class for, I don't even remember what reason, but I did. So if you want to use the code as it is here, you will also have to modify it. You don't have to use vector3, but I did just because it simplified some math later on. So to do that, you need to make sure that you have this member variable here called m_f. And to prevent your code from breaking everything that we've written up till now, I did something a little bit smart here and created a union between these variables and this other variable called m_f. So let me show you how to do that. If you create a union like this, I create a variable here called float m_f, which is 3. So this is actually an array of 3 floating point numbers. But it's in a union with a structure that has 3 floating point numbers split up this way. So it has fx, fy, and an fz. Now what a union does is it lets you say the memory allocated to this guy is the same memory that's allocated to this guy. So anytime I access m_fx, that's the same thing as accessing the memory called m_f bracket 0 here. If I want to use fy, then that's equal to f1 over here. And fz would be equal to f2 over here. So a union lets you split up the memory to be named different things, but still accessing the same address space inside memory. So because of this, we can continue using these variables here, but if we ever need to access these variables as an array, we can just use this variable up here. And that's exactly what I did over here. Because fread needs an array, I can pass in the array this way, but then whenever I need to work with the vector3 data, I can still use my m_fx, fy, and fz parameters. So make sure you make this change here. Now, it would be nice if we could actually go and compile this code, but if you try, you'll get a whole bunch of error messages because, well, actually you only get one, because it cannot find this .h file. And then if you create this .h file, it'll say it cannot find the next guy, which is this poly.h file, and then it can't find this guy. And then once you do create these guys, it'll complain because we're using functions within each of these classes, but we haven't actually incorporated these into our game engine. So in the next VMK, what I'm going to do is actually implement this class so that you can see what we do behind the scenes with all the material data. Then we're going to go in and implement the next guy and then the next guy. And then once we have all 3 of those, we can then come back into here, recompile this to see if there's any error messages and continue working forward. So I tried splitting this up slightly so that it's a little bit more manageable in terms of programming it and writing it out inside of the compiler. There's a lot of repetitive code here from the previous VMK, so make sure that if I did do something different that you don't understand from the previous VMK, you do ask, and I can clarify things up for you. Once again, if you are having any problems, feel free to go to the community section on the website and post any questions you have pertaining to any specific VMK. And if you do have something to show off, basically if you've done something and it looks pretty cool and you're kind of proud of what you've done, feel free to go under the show and tell section here and post your code or your results for any other people to see that are also working with the same game engine. And you guys can sort of share resources and see what you guys can come up with. I just finished editing the video and I was about to release it to you guys, but then I noticed that there were some memory leaks in the code. So before actually releasing it to you guys, I want to go back into the Caligari file.cpp and show you how to fix these memory leaks so that when you guys program it, you won't have the same problems that I ended up having. So to do this, starting off in Caligari file parser function here, there's only a couple things you need to change. You'll notice that anytime I use the new operator and there was an error message caused, I needed to go and delete the memory that was allocated to us using new. Well, I didn't really stay consistent, and if you scroll down here, you'll see over here I call delete poly h. You could go and you use the save delete macro like so, just so that after you delete the guy, then he's also set to null. So let's just do that here quickly. You know, I should just cut and paste the whole thing. Probably go faster. Okay, now those won't give you any memory leaks because you do actually delete the memory properly. The memory leaks do show up somewhere else, and if you scroll down here, there's nothing in material. All the problems were inside of the shader box functions here. Okay, the first part, if we scroll down through here, again we have just delete being called, so let's change this to save delete. Then scrolling down a little bit more, here whenever we allocate memory for the parameter name, if there's an error, we call save delete for the shader box, but we also need to call save delete array for the shader name. Because if you scroll up above here, we did allocate new memory for the shader name here, but we forgot to deallocate it. So make sure you add this extra shader name here to be deleted as well. And if we continue scrolling down, under case number 10, when there's an error, we need to delete the shader box, but we also now need to delete the shader name and the parameter name. So make sure you go in and add that. And scrolling down here, same thing if this guy fails. But now you also need to delete the memory that was allocated here for this name up here. So we just call save delete array, and we delete said name right here. Then located down here, we can change this guy to use save delete array. And scrolling down to the default case, whenever we have an error message here, we need to delete all three items as well. The parameter name down here, we can use the save delete array. Oh, double comment here. And we can repeat the same process for the shader name down here. And that's pretty much it. So make sure you go through and you add in these extra deletes for the missing parameters that I forgot to add it the first time through. And one other thing I wanted to just make you guys aware of, you'll notice that inside of the poly, right here, I create some new memory for the name. And then I go ahead and I null terminate it and stuff, and then I create a new poly, and then I change the spaces to underscores, and I set the name inside of the poly. But you'll notice that after there's error messages down below, I never go ahead and delete the new memory that gets allocated here for the name. The reason for this is not a bug. It's because after I set the name inside of the poly is now responsible for the name. So the poly will actually delete any memory that is allocated for the name inside of its destructor. So just by calling safe delete for the poly, this will take care of deleting the name that the poly is associated with. You'll notice that we don't do that in here in the shader part because the shader name doesn't actually get saved inside of the shader box data type. Same thing with the parameter names. Those guys are handled slightly differently, so that's why whenever we delete the shader box, we need to delete the shader name and the parameter name manually, the way I've shown it here. Okay? So just one thing to make sure you go and correct, and that's it.